Good morning. So today we're going to be starting chapter 8 now, where we're going to talk about structures of various types of compounds. So let's go ahead and get started there. So just a reminder, you have an exam next Monday on 6 and 7. That would be on electron configurations in light, and then on the periodic trends we talked about in class. So that's coming up next week. All right, and so this material that we're going to start today is not on that exam, but it'll keep going on. So this is going to be kind of like, I don't know, structures of compounds. And kind of the first thing we're going to look at is ionic bonds, and then we're going to spend the majority of our time on covalent bonds. So we're going to see that covalent bonds, we have a lot more to talk about, and there's also far more covalent compounds than there are ionic ones, so it's a bit more important, suffice it to say. And just a heads up, if you're planning to take organic chemistry whenever it's next offered, this chapter is super important for it, at least with the covalent compounds. So the ionic ones, not so much, but the covalent ones are super, super important for organic chemistry. So first things we want to do is talk about Lewis symbols. Or atoms and ions. And how we typically do this is we will take a particular atom and we will indicate its valence on it. For example, we know sodium has 1 valence electron, boron has 3, oxygen has 6. Although technically I should redraw that, and so you can see the process. We always want to start off unpaired, and then we start pairing them off. So oxygen has 6 valence electrons, as we know, and sodium has 1, boron has 3. So we represent these as the element symbol with some electrons, represented as dots here, around them. And so these represent how many valence electrons they have. And we're going to see that, for example, we have some more. I'm going to just draw this one real quick. So chlorine. We can see pretty clearly what's going to happen when we put these two guys together. We know sodium is going to lose an electron, chlorine is going to gain one, right? And so what that would look like would be something like this. Technically, if we really wanted, we could also indicate sodium's electrons, but now it's got a full set of 8, right? Because it resembles, the sodium ion represents neon electron configuration, and chlorides represents, or is the same as argon, right? And so put together, both of those you can see have 8 valence electrons then. And that's the ideal number. That's why sodium makes the +1 charge, why calcium makes +2, why aluminum makes +3, why sulfur makes -2, oxygen makes -2, is to get to 8. This is something called the Octet Rule. And that's going to tell us that most atoms are most stable with 8 valence electrons. Most of them are. Of course, there are some exceptions. For example, the first row of the periodic table where we don't even have close to 8, some of them have just 2, and that's just fine. So some exceptions. Of course, hydrogen, helium are happy with 2. These three are all stable, and we could even say beryllium too. They're stable with two valence electrons, just the 1s electron. So lithium will lose its 2s electron, become 1s2 as its configuration. These are all stable elements with two electrons around them. We're going to see beryllium is also stable with 4, be stable with 4 as well. And then boron is stable with 6 valence electrons. So these are the exceptions, and they're all kind of the first couple of elements, the first 5 elements. So after that, once you get to carbon, it really wants 8. And so nitrogen and all of them want 8 electrons. So they're going to be doing things to get those 8 electrons. These first 5, though, are kind of exceptions. Beryllium especially is happy with 2, but it's also happy with 4. So it's a little bit weird of an element, but it can do either way. Okay. So those are a few exceptions, and again, they're all those first 5 elements. So that's what we're going to look at here. Okay. So we're going to see that most things will do what they can to get there. And so when we see that ionic bonds being formed, if we take that sodium if we want to see kind of a reaction for what's happening here, we saw that if we take a look at what's actually happening, we know that sodium is becoming sodium ion, and it's losing an electron. And we know that chlorine, which again we typically indicate as half Cl2, right? We know that it's going to be accepting, right? And we saw we had terms for this, right? We saw that the first reaction, sodium losing an electron, becoming sodium plus, is what we call the ionization energy. And on the other hand, chlorine gaining an electron is electron affinity. And we have delta H values for both of these. And we're going to see that delta H for sodium, see if I have this around here somewhere. I do, 496. Positive, right? Ionization energy is always positive. And if we look at for chlorine, we saw that that was negative 349 kilojoules per mole, right? And so we're going to see that if we were to just kind of put these two together in the manner of Hess's law, if we add those two reactions together, just like what we do with Hess's law, we'd cancel out the electrons, we would get our blue equation here. We would see that if we try to do the total delta H, we just add these together. And that number is going to be 496 minus 349, 147. Wait a second, this is terribly endothermic. What's happening here? Well, it turns out that these reactions are not quite complete, as it were. We technically have, in this, we have not NaCl solid, but we have sodium ion and chloride ion. And so really that this represents this equation. The equation that this one represents is having these ions separate. And so we see that there's also an energy to put these guys together. And that energy this is called the lattice energy. And this is the energy that is associated with having two ions come together to form a lattice. Right? A lattice is just a repeating structure. So it's going to show us, how we typically see sodium chloride, sodium, chlorine, sodium, chlorine, sodium, chlorine, and so on. We'll talk about that more in chapter 12, I think, when we start looking at structures of solids. And we see that this value is, for this particular reaction, is a negative 788 kilojoules per mole. Strongly exothermic. This is very favorable to take two ions and put them together. So this positive number that we got here, the endothermic portion of this, isn't quite the complete picture, because we really have a third component, which is the lattice energy. And so as a result, our total reaction, so if I go ahead and write this out again, if we take so putting these two reactions together, this was 147. That's negative 788. So if we want to put these reactions together, we would just need to add their delta H's. Which gives us, this down here somewhere. Let's see, I can do the math. 146. Negative 641 kilojoules per mole. So overall for this reaction, it is indeed highly exothermic. So we would expect this. And we should hopefully see, if we went to the energy of formation, delta HF, we should see that this is the value we'd get for this. So there may be some slight differences depending on the states of matter of the atoms involved, but that's what we're looking at for this. So making ionic compounds is typically quite exothermic because of this lattice energy. So the ionization energy and electron affinity themselves probably will not produce an exothermic reaction, because those ions themselves, they don't lose energy by doing this. The chlorine does, but the sodium doesn't. And so you have to have this kind of reason to have this reaction go forward. And we know that sodium plus water reacts pretty violently. We saw videos on that, right? Reacts even more so with chlorine. So chlorine and sodium react very strongly together. And the reason for that is this lattice energy. So that's the only kind of new thing that we're putting in here. So when you put ionic compounds together, you have a lattice energy component. And looking at the lattice energy is going to be useful for us to talk about as kind of a start to talking about bond polarity later on. Let's give some examples. The lithium fluoride has one of negative 1030, 834 for lithium chloride, lithium iodide at 730. Look at sodium fluoride, 910. Sodium chloride, we just did 798. And Sodium iodide is going to be 682. So there's a couple things we probably notice here. If we take a look at the size of these things, oops, we know that of all the atoms present here, lithium and fluorine are the smallest ones, right? They are in the highest level of the periodic table. So notice here that we have our smallest ions, and here we have our biggest ones. And if we take a look at the lattice energy, as we keep putting on bigger halides, fluorine, chlorine, iodine, in both cases, our lattice energy is going down. Or up, I suppose, because it's negative, but it's getting smaller, absolute value-wise. There's less energetically favorable reasons to get together when you have bigger atoms or ions, and we'll see why. So, and as we see here, as we replace lithium with sodium, sodium is a bigger version of lithium, right? We again have a decreased absolute value of our lattice energy. So this is the smallest ions, but the biggest, we'll say most exothermic. Got the most exothermic lattice energy. This one is the sodium iodide is the biggest ions, and it has the smallest, least exothermic. Energy. And so we see here that we're going to be able to predict this by using one of Newton's kind of relationship. And we see that kind of the electrostatic force, so how well ions are attracted to each other, is related to the charges, so some constant, over the distance between them. Actually, this is more for gravity. We'll say distance or diameter of the whole thing. These represent the charge. Kind of just how big it is. It's kind of the distance in between them. So here's D represents that that value. So D is the kind of it's the added radius of both ions put together. That's D. So we see that the force of electrostatic interaction, aka the lattice energy, we can say, is related to the charge and how big the ions are. So we're going to expect that if we have a larger charge with smaller atoms, that's going to give us the biggest electrostatic happiness, as it were. So the point, you're not going to use this equation, mind you, but let's look at what the equation tells us. This equation tells us as your charge increases, your attraction other ions increases. That's what the electrostatic force is. And it also tells us as the size increases, the attraction goes down. So we have the opposite case here. And so if we take a look at a couple more examples, we can see that. If we take a look at lithium Well, let's look at sodium. Sodium chloride had negative 788. Magnesium chloride, on the other hand, is 3 times as much, right? And the reason for that is because magnesium not only is smaller, but also magnesium 2 plus is more charged. Chlorine 0 are the same, right? So we don't need to compare them. But we see here that magnesium, remember that the isoelectronic series tells us that magnesium ions are smaller than sodium ions. And so, point one, they're smaller, so the attraction goes up. So, same thing. So, sodium is bigger, so its attraction goes down. Magnesium is smaller, so the attraction goes up. And then, as charge increases, we also increase our attraction. Magnesium has twice the charge that sodium has, so we're also expecting the attraction to go up. And so, as a result, yes, we see a much more exothermic lattice energy for magnesium chloride than we do for sodium. All right. So that's the idea here. And if we keep going, if we take some like supercharged things, 3 plus 3 minus, we're looking at lattice energy of negative 7547. So it just keeps going. This is another trend, you could say. It's rather a trend that incorporates 2 other trends, but that's the idea. So the bigger your atom is, the less your attraction is going to be. So if you want high attraction, you want small atoms with a lot of charge. So N3 minus is relatively small, and it's got a negative 3 charge. So we're looking at definitely a relatively high lattice energy for scandium nitride here. All right, so that's the trend. That's what we're looking at here. All right, so that's kind of what you want to be looking at with this sort of thing. And how this kind of fits in all this is it's taking in the ideas of ionic size and kind of the predicted charges that things would have based on their electron configurations. So it's really, this lattice energy idea is a synthesis of chapters 6 and 7 topics. So electron configuration, all the valence electrons happening here, and then the size aspect as well. So putting those things together, we see that we have this trend, as we can say, for lattice energy. And so this is the reason that this is the reason that some compounds soluble in water. And we see generally this is because they have high lattice energy. I guess we could say negative. So it depends which one is going to be the more exothermic process. If the lattice energy is more exothermic than the solvation energy, we're going to see it's not so simple as this, but this is a trend. Let me rephrase it a different way because I don't want it to seem as though it's just a numbers game. If this is very exothermic, it is unlikely to dissolve. We'll say it that way. So it's unlikely to dissolve with 2 L's in unlikely. Unlikely to dissolve if it's very exothermic. Because by dissolving it, you're taking now those ions and separating them again. So you have to overcome the lattice energy, which can be tough for the scandium nitride. We're expecting that probably is not going to be soluble, right? Look at how high its lattice energy is. Though there is an energy benefit to surrounding ions with water. There is an energy of solvation there that is useful. But you'll see that if you take Gen Chem 2, that will also have an entropy term, measure of disorder, and that's going to be really the driving force behind making a solution. So you'll see that it's multiple things coming together to overcome lattice energy. And so we have to see what's going to win out there. Alrighty, so that's ionic stuff. We're not going to really focus on ions for probably the next 2 chapters now, so we're going to kind of leave them here with this idea of the lattice energy. So we saw, as a result, even though the ionization energy and electron affinity overall produce an endothermic reaction, the lattice energy allows this reaction to happen because there is a strongly favorable reason for these two ions to form and get together. And so overall that does produce a strongly exothermic reaction, and so we get a reaction to happen. Alrighty. Don't forget this relationship either, by the way, this idea of charge and size. This will be important later when we talk about bond polarity. All right, so don't forget this kind of equation. Again, we're never going to use that equation mathematically speaking, but it's important that we understand the relationships there. Okay, so let's talk about covalent compounds. And again, if you're going to take organic chemistry, this is definitely something you're going to want to be very good at eventually. So let's talk about covalent compounds. We're going to see that the word covalent, co means together, right? That's a good word. Cooperate. There we go. Operate together. That is what cooperate means, right? Valent refers to valence electrons. So these are going to be molecules that share electrons. Compare this with ionic compounds, where electrons are kind of given away. So electrons are given away in ionic compounds, but with molecular compounds, they are shared. And we're going to see what this looks like. I'll give you a couple of examples, and then we'll learn how to make these. We're going to see this is a molecule of methane. Got 1 carbon, 4 hydrogens. And we're going to see how this works is that each of these are going to be sharing electrons. So each hydrogen is sharing a pair of electrons with the carbon. And as a result of the sharing, I'll write that out. So each hydrogen is sharing 2 electrons with carbon. Recall that hydrogen wants 2 electrons to be stable, and that carbon wants 8 electrons to be stable. Right, that octet rule. And if we see here, we see, well, each hydrogen has 2, because it's sharing them. It's sharing 2 electrons with carbon, so it's stable. we see that carbon wants 8 electrons, so it's sharing 4 pairs of electrons, 2 with each hydrogen. And we're going to see that we typically will draw this like this, where these lines here, these indicate a shared pair of electrons. Right? And it shows us how these elements are able to come together so that they share their electrons together and as a result are able to stabilize each other. So through this way, I mean, if we consider what carbon has to begin with, it's got 4 valence electrons. We have all these hydrogens with just one. And so what happens is these hydrogens are going to all share their electrons, all going to share them, which gives this kind of shared idea here. We're going to see a couple of ways to make Lewis structures. I have quite a few. I have 2 major ways to show you, and both of them will work. But in each case, you'll have to do some double checking. Just like with making ionic compounds, right? We had the like algebra method versus the crisscross. It's the same idea here. We're going to have some ideas. So these happen because these atoms share electrons, and so these are called Lewis structures. Okay, and so we're going to see how to make these. However, I do want a couple more examples. I want to show you a few things. This is another one. These are a couple of examples as well. And let me tell you what all these mean. This means 3 pairs they're shared between carbon and nitrogen. And here is 1 pair shared. So remember, each of these lines represents 2 electrons. And as a result, we can see here that that carbon is going to have 8 electrons. It's sharing 6 with nitrogen on one side. It's sharing 2 with hydrogen on the other side. As a result, it will have 8. Nitrogen, as we can see, has 3 shared pairs, so it's got 6, but it also has 2 electrons just to itself. We call this a lone pair. And those are not shared electrons. So those are just electrons that are on nitrogen by itself. And so it has a pair of electrons, 2 electrons, and it's got its 3 shared pairs, overall giving it 8. And we see it's going to be the same case here. This is now 2 on either side. So this carbon is sharing 2 pairs on either side, so it's got 8 total electrons. And the nitrogen or the oxygens each have 2 lone pairs each, which is 4 electrons. So the oxygen has 2 lone pairs, that's 4 electrons, and it's got 2 shared pairs, which is another 4 electrons, giving the oxygens 8. And so we're going to see here that all of these atoms are stabilized this way. And indeed, I've shown a lot of them with carbon in the middle because that's what organic chemistry is. Except it's not just 3 atoms at a time or 5 atoms. We're looking at dozens of atoms at a time. But often you'll see carbon will be what's called a central atom in a Lewis structure. Alrighty, so let's talk about how to make these things. I'm going to give you 2 methods. And you're welcome to use whichever one you like. So they'll both work. Um, just make sure that don't forget your lone pairs. That's the biggest mistake that people do is they forget their lone pairs. It's important that we have everything shown on a Lewis structure. So we need to show that all atoms are satisfied. Alrighty, so let's see, how do we make them? How to make Lewis structures. Let's start off with methane. Easiest one, perhaps. We have two methods. The first method I'll teach you is counting the valence electrons. Oops. So we have a method of counting valence electrons and distributing them. Option two will be the kind of connect the dots method. These aren't formally named methods, but we'll see how this is going to work. Both of these do have some considerations to keep in mind. With this method, do you have to worry about formal charges? Um, um, need extra watching, extra attention, we'll say. So these are the drawbacks with these. Is with the first one, you're going to see that you'll end up with what are called formal charges more often that you'll need to resolve. And then the second method, you're going to have to just be extra careful if you have second row elements involved. And so there's not too many cases where you will need to, but sometimes there are. So, all right, it's a little cold in here. We're getting into fall. How exciting. So let's go with the valence electron counting and distributing method first. We'll do that one first. Method one. So for this one, you want to add up all the valence electrons. That is obviously, if we're going to do valence electron counting, it would make sense that we would count our valence electrons. So that's the first step. We would need to subtract electrons if something is positive, and we would need to add electrons if negative, right? And so this means, for example, if we had carbonate that's got a negative charge, so we would need to add two electrons because we have this negative 2 charge here. So the total valence for this ion would be 4 plus 3 times 6 plus 2, which is, I can do the math, 24. So remember, the group on the periodic table tells you how many valence electrons you have. So carbon group 4 or 14, depending on your periodic table, has 4 valence electrons. Oxygen in group 6 or 16 has 6 valence electrons. And then we have to add 2 because we have a -2 charge here. So you will need to add or subtract electrons as necessary if you have a positive or negative thing. All right, so that's step 1. Step 2 is assemble the skeleton. And that means that you're going to take your central atom and draw a single bond all outer atoms. For this, remember that each single bond is 2 electrons. So I'm gonna have to do this. Okay, well I said we're doing methane. So methane's sorry, I should slow down. Let's look at methane. This will be an easy example. Methane has the valence electrons of 4 plus 4 times 1, which is 8 valence electrons total. And so if we're to assemble the skeleton, we're going to draw our central atom. Usually that's the first one. Usually your first atom is the central one, generally speaking, but we'll look at that in a sec. We want to make a single bond to each outer atom. And so we had 8 electrons to start with. We've just used 8 electrons. We have 0 electrons left. And it's important that you keep track of how many you've used through this method. That's curious. So with this, we're out of electrons, but we're okay. We're done because this was a simple example. That's all we needed to do. Was we would assemble our skeleton, and in this case, the skeleton is the Lewis structure. All right. Step 3, which is not applicable here, is, well, I guess it's applicable. Check if all atoms have octets. Again, recall you would just need to make sure that all atoms are happy in your skeleton. And you'd see in this case, yes, carbon has 2, 4, 6, 8 bonds, or 8 electrons on it. Remember, each line there is 2 electrons. So that carbon has 8 electrons, it's happy. Each hydrogen has 2, they're all happy. And so then we need to consider what to do next. So if the central atom is missing then you make double or triple bonds. And then step 4, minimize formal charges. This is not something we're going to look at right away. I guess we will, but we're going to look at step 3 first. All right, so these are the steps for this procedure. We're going to see that the other method bypasses all of these for the most part. But it's still important that we do this. So let's take a look at CO2. Let's look at CO2. Let's count the electrons. We have carbon plus 2 oxygens. which is 12 plus 4 is 16 electrons. Ooh, I forgot a step, actually. Whoops. All right, step 2.5, because I realized I forgot one, because it wasn't applicable here. 2.5. Give extra electrons to outer atoms first, and then the center one. So we're going to give extra electrons that we have to the outer atoms after we have made our skeleton, and then we're going to add them to the center afterwards. So we give priority to outer atoms. So let's take a look at that. So that was step 1. Step 2 is the skeleton. And so we draw our central atom, our outer atoms, and a single bond in between them. All right. So drawing those 2 single bonds will take up 4 electrons. So we have 12 electrons left. So 2.5, as these are arbitrarily numbered, I can do whatever I want. Step 2.5 is now we're going to distribute outer atoms, and then to central atom. So we have 12 electrons. We want to make sure that everything has a total of 8, right? So we're going to start with the outer atoms. So here we go. This oxygen needs 6 more to be happy. So that's 6 electrons. We've got 6 left. And this oxygen will also take 6 to be happy. And we have no more electrons to give to carbon. Remember that we want our outer atoms to have octets, right? So we have to make sure that we give them enough so that they have 8 electrons. And so now we're going to go ahead and check our structure. We're going to check them all for octets. And we see, aha, this oxygen has 8. This oxygen has 8. This carbon has 4 only. Very sad. Very sad carbon. So what we do to fix this is we take a lone pair and convert it into a bonding pair. All right, so if, remember, central atom has less than 8, then we need to make double bonds or triple bonds. So what we're going to do is let's try doing this. Let's go ahead and take this pair of electrons and turn it into a double bond instead. All right, we're going to share that extra pair. And let's see what happens. Now I'm going to be very careful with my color coding so we can see all these different bits. Well, it looks like if we are going to check, we have 8, we have 8, and now we have 6 on the carbon. So still not happy. So we have options here. We could either make a double bond on the other side, or we could make a triple bond. Let's make a triple bond, because why not? I feel like it. And so if we make a triple bond, and now we check, we see everything has 8. All right, alternatively, though, we could have instead done it this way. We could have shared one from the other oxygen instead. And so, what we're going to see is that one of these structures is better than the other. Sometimes you'll have multiple correct structures. Um, and we're going to see that when multiple structures are possible, this is a phenomenon known as resonance. And so we can distribute electrons in different ways. And that's a phenomenon known as resonance. So we'll talk about resonance in a little bit. Let's talk about why one of these is better than the other. So we're going to introduce something called formal charge. The formal charge on an atom is going to be the valence electrons for that atom minus the number of bonds. I really need more space for this. I'm going to formal charge is equal to the valence electrons for the atom minus the number of bonds minus the number of lone pair electrons. So let's take a look at all three of these atoms. So I'm gonna copy this structure so we can analyze the formal charges. Actually, I'm gonna copy both. So let's see what we get here. So if we look at this oxygen, it's got 6 valence electrons minus a single bond, one bond, minus 6 lone pair electrons equals -1. So that tells us that this oxygen has a formal charge of -1. The carbon has 4 valence electrons, minus 4 bonds, minus 0 lone pairs is 0. It's neutral. The other oxygen, though, 6 valence electrons, minus 3 bonds, minus 2 lone pairs electrons, and plus 1. So overall, that oxygen has a positive charge. The one on the left has a negative charge. Those are formal charges. They are destabilizing. We don't like formal charges. Notice, however, that both of them, they cancel out, right? We have a -1 and a +1 in the same molecule. They cancel out. Overall, our molecule is neutral. But we're going to see that a better Lewis structure is one that minimizes formal charges. And so we're going to see that this structure here, if we look at this oxygen, we have 6 valence electrons, minus 2 bonds, minus 4 lone pairs electrons is 0. We're going to see that all of these have formal charges of 0. And so as a result, this is a better structure. This is a better structure here. Right, because it minimizes the formal charges. So some of this Lewis structure work is somewhat trial and error. You figure it out. You try things out, follow the steps. If you end up with formal charges, think how you might be able to redistribute those. A negative formal charge means you have too many electrons on an atom. A positive ones mean you have too few electrons. So the atom would prefer to have more or less. So these formal charges are very important for us to analyze when we're looking at Lewis structures to see if we've got the correct one. Sometimes formal charges are unavoidable. which is why we have things like carbonate. Here, let's do that. Let's do carbonate. The fact that we have a negative 2 charges is going to tell us that this molecule has either one, two formal charges of -1, or one formal charge of -2. And in fact, this is not a molecule, this is an ion. So because it's a charged species, we know that those formal charges are what's going to be that charge. We saw that with this one, we had negative and positive cancel each other out. Not a problem. But we see that the carbonate ion here has a formal charge of, or there's a total of -2 in their formal charge. So that can either be on one atom or two atoms. Formal charges are always integers, so you can't have like, well, I say that, but I'm going to just contradict that as soon as I'm done with the Lewis structure. Um, because of resonance, because multiple structures are available, you might see in non-integer formal charges. But in a particular Lewis structure, one structure only, you will only have integers. If you're looking at combining multiples into one, then you'll have resonance, and then you have potentially non-integer values of formal charges. But let's not worry about that for now. So let's do the total electrons here. We have 4 from carbon, 6 from each oxygen. We have 3 of those, plus 2 because we have a negative charge of 2, and that was 24 electrons that we have to work with. Generally speaking, by the way that I started my skeleton, I put them on the opposite side of each other. Usually if you have 2 outer atoms, that's how you want to do it. You want to put them on the opposite side of each other. If you have 4, you put 2 on the sides, 1 up, 1 down. If you have 3, typically you'll see it drawn this way, where you have 1 on the bottom. This is just typical. You can do it, put yours on the top, I don't care. Have fun. And we're going to see next chapter when we talk about shape, it's all going to get changed anyway. But this is kind of the convention. So we want to draw a single bond to each one. All right, single bond to each one takes 6 electrons. We have 18 left. Let's start giving some out. We have 12 electrons left. Let's do purple. We've got 6 electrons left, and we're going to do, how about red this time? We have none left for dear old carbon in the middle. Oh well. So let's check now. We have 6 electrons on carbon, 8 on any of the other ones. So we only need to make one double bond. A double bond will add 2 electrons to the carbon. So we have options. We could put the red one in, or we could put the purple one in, or we could put the blue one in. I'm going to just draw one at a time. Let's draw the red one. We see that doing so will give us, I'm going to just do this real quick. That'll give us that way. And if we look at the formal charges, actually, let me draw all 3 structures first. And then we'll worry about that formal charge business. So don't forget your lone pairs. All right, so there they are. These are the 3 structures we get. All 3 of these are equivalent to each other. there is no reason we can take it from the left but not from the right. They're equal. They're all equivalent to each other. These are what are called equivalent resonance forms. They are all equal to each other. And if we made this really spatially correct, we would have it at 120-degree angles instead of 90-degree angles. And we would see that we could just rotate this thing and they would interchange. And so they're all equivalent to each other. So there's no reason that one is better than another. So this molecule happens to have 3 equivalent resonance forms. This previous one, the CO2, it had 3 technically as well. You have one with a triple bond to blue, one with a triple bond to purple, and then one with a double bond to each blue and purple. And so we didn't draw the one that had triple bond to purple, but we could have. We would see it's the same structure as the one on the left here with the formal charges. So those two would be equivalent to each other, but we would have a better resonance form, which is the one that has no formal charges, which has the double bond to each blue and purple. So the number of resonance forms is just kind of the number of options that you have of how to make your double or triple bonds. And so depending how many different things you have going on, you may have multiple resonance forms possible. All right, so in this case, for the carbonate ion, we do indeed have 3 resonance forms, and they're all equivalent to each other. There's no reason that one would be better than another. And so if we look at the formal charges, we see that this one would be -1. In this case, they all will have the same number of formal charges. It's just where those happen to be located. And so we know that we're going to have an overall formal charge of -2 anyway. So we knew that we have to have formal charges. And we see that all of these have the same number of formal charges. So they're all equivalent to each other. If one had more formal charges, then that would be a bad thing. But they all have the same number of -1s. All right? Formal charge of -1 is always better than 2 -1s are better than a -2, single -2. Although that's not possible with this particular molecule. So, good stuff. We're going to see that these 3 combine, that you'll sometimes see it. Sometimes you'll see this thing as drawn this way. You'll see it sometimes drawn this way, where you have a -2/3 formal charge on each one, which gives you a total of -2 overall. This is a hybrid structure. And this just combines the resonance forms. So we saw we had options of making a double bond with any of those. And if we look at them, let's look at just one atom at a time here. Let's look at this rightmost atom. In 2 of our Lewis structures, it had a -1 charge. In our third Lewis structure, it had a 0 formal charge. And so the average for that would be -1 plus -1 plus 0 divided by 3, which is -2/3. And so that's where these numbers come from. It's the average formal charge for them. I'm not going to really worry too much about you drawing these hybrid structures, but I want to show them to you because you will see them. If you Wikipedia these, you'll see strange hybrids sometimes. And so that's where those come from. But if you were to just give me a Lewis structure, I would accept any one of these. If I just asked you, give me a Lewis structure for carbonate, any one of these is fine because these are all equivalent to each other. So you're welcome to give any one of these that you like. So take your favorite side of this skeleton and decide which one you want to work with. We're gonna see that. Okay, I'm gonna teach you the next method first, and then we'll analyze this a little bit more. All right. So first, let's go ahead and look at the other method, method 2. And so there are steps for this one as well. But in my opinion, it's a little bit faster. It's a little bit easier. Um, and so I like it this way. But you are welcome to use whichever way you like. So step 1 is draw all atoms with their valence. So if we are going to do CO2, we're going to draw all these atoms with their valence electrons. Doesn't matter how you draw them. I'm going to just draw them this way because that's going to help us out in a little bit. And then step 2 is you're going to add electrons to outer atoms if you have a negative charge, or you are going to remove electrons from the central atom if you are a positive ion. In this case, CO2 has neither, so we're going to skip this step for now. Connect the dots to make octets. So what that looks like is we'll be like, aha, well, we're going to connect those, we're going to connect those to satisfy your outer atoms. That's kind of the big part. We're going to satisfy our outer atoms more than the central atom. So satisfy your outer atoms by connecting the dots. We're just going to say, aha, we have unpaired electrons here. We're going to pair those off. And how this works is we only need to pair off let me just do, instead of we need to connect unpaired electrons. So if we do this, what this means is that we have C double bond O. Oxygen still has 4 lone pair electrons. Those lone pairs are still there. And then I use blue for the other one, so we'll be consistent. And so that's our structure. We're done. It automatically will minimize formal charges. This method automatically minimizes them. So with the previous method, depending on which connections you make when you're making double bonds, you need to double check for formal charges. With this method, you typically do not get formal charges unless they are things that can't be resolved. All right, so you always want, you're going to pairing off unpaired electrons by combining them between the central atom and the outer atoms. If we take a look at carbonate, we can do this method for that. Let's do this method. So we don't need to count anything. First step is draw all atoms with their valence electrons. The carbon has 4. Remember, don't start pairing off until you have more than 4. So technically, I'll draw these all separate. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, because this is negative, we need to give 1 electron to 2 outer atoms. So here we go. 1, 2, done. Those are my blue electrons. That's the -2 charge. And then we just need to connect them. We need to make sure that our outer atoms pair off their electrons. So we're going to start pairing those off. And lo and behold, we end up in this case with the following structure. I'm going to draw these dots real big so we can see them all. And thankfully, this even tells us the formal charges. The atoms we gave the electrons to are the ones that will have the formal charge. So it does the work for us. So if we gave electrons, I'm going to actually draw those as blue again. So those electrons that we gave tells us that that's where the formal charges are going to be. We gave 1 electron, so those atoms will have a -1 charge. So I think it's an easier method, faster, minimizes them automatically, and even so, it will tell you where those formal charges are. Whereas with this one, we would still need to calculate where our formal charges happen to be. And I just did it for us real quick in the interest of time, but with this, we get the same thing. And so because we had the choice of where to give those extra 2 electrons, we could have given them to the left one and the bottom one, and then we'd have our double bond to the right one. We'd still get resonance forms. So we had a choice. So I decided to give them to the bottom and the right ones in this particular example, but I could have chosen other ones. And that's the idea of the formal charge. If we take a look at something like ammonium, let's do it both ways. Method 1. We have 5 plus 4 times 1 minus 1, which is 8 electrons. If we go ahead and draw them, we will use our 8 electrons. We have none left. Check for octets. Everything's happy. But don't forget, since this is a positive ion, we do need to have a formal charge of +1 somewhere. So we're going to want to check. It's never going to be on hydrogen. I'll just tell you that hydrogen has never got a formal charge on it. So let's look at nitrogen. We're going to see that nitrogen will be 5 valence minus 4 bonds minus no lone pairs. It has the +1 on it. If we look at connect the dots, we want to draw them all out with their valence. And notice, because this is a positive charge, we will remove 1 from the central atom. So poof. Oh, I erased my central atom. That's not good. So we removed one from the central atom, so that's going to tell us already we have a positive charge on the central atom. So it's going to have a +1 charge. We just need to pair everything off. 1, 2, 3, 4. And we end up making our... We know that there's going to be a formal charge on nitrogen there. All right, so that's a positive one. Get a little bit easier, I think, in my opinion, to do the right side, but we'll do it again. We'll do another one where we compare them, and I think it'll make it a little bit easier to see the difference between the two methods. All right, let's do this one. Let's do sulfate. All right. Method 1, we would take sulfur plus 4 oxygens plus 2, which is 6 plus 4 times 6 plus 2 is 32 electrons. We've got to put them out here. We want to do single bonds to all of them, so that'll be 8 electrons. 24 left. 1, 2, 3, that's 6. And I hope it's okay if I go ahead and just zoom through the rest. The 18 we're going to give around to the other 3, right? They all need 6. We have 3 of them, so that's 18 electrons. We have none left to give to sulfur, which is okay, because sulfur only wants 8. If we check octets, everything's happy. Everything has 8 electrons, but formal charges is something we're going to have to check. And you see that all of these oxygens, it's got 6 valence electrons minus 1 bond minus 6 lone pair electrons. All of these guys have -1. And if we look at the sulfur, it's got 6 valence minus 4 bonds minus no lone pairs plus 2. And so to minimize that, we need to combine some things. So to minimize the formal charges, we can minimize by making double bonds. Remember that a negative formal charge means too many electrons. Positive formal charge means too few electrons. And so, as a result, we're going to want to give sulfur some more electrons by moving some inwards. And again, here it's silly to make a triple bond when I can make 2 double bonds. 2 double bonds is almost always better than a single triple bond. So if we do that, we'll see that we'll end up with if we do this, we have -1, -1, which is okay because sulfate has a -2 charge overall. And so this is going to be the better, and we'll see. Let's compare with the previous one that we had. So option 1 had us with minimized formal charges. However, we see that now sulfur has exceeded its octet. On the other side, we have the opposite. We have many formal charges, but our sulfur has an octet. So, which one's better? Unfortunately, this is still a topic of debate. There is evidence for both. And so, I get to make the decision that for our class, we are going to do the one that has the minimized formal charges. So, this is going to be the one that wins for us. Right? This is the winner. So I'm going to say that minimizing formal charges is more important than maintaining octets. But we must keep something in mind. However, only something in period 3 or higher can have more than 8 electrons. All right, so anything that's in period 3 or below can go more than 8. It's called an expanded octet. Also called a hypervalent species. So this sulfur here has 12 electrons, and that's okay because sulfur is in period 3. And there's two explanations for that. In period 3, sulfur has technically access to the 3D orbital, and so it can dump electrons into 3D, even though that is higher. So it has empty orbitals, so we can store some electrons there, extra electrons. Two things in period 2 don't have, there's no 2D subshell, so there's no place to put extra electrons. We have to also consider sulfur is bigger, so it has more room to accommodate more bonds. So that's the reason. So sulfur is large plus access to 3D orbitals, empty ones. And so it can accommodate extra electrons. All right, but something like nitrogen can't. All right, real quick, I'm going to do the second method with the sulfate. Okay, let's give some extra electrons. 2 extra electrons, because sulfate has a -2 charge. So boom, we know those will be -1. Connect the dots. Satisfy your outer atoms. We don't care about the inner atoms. We're okay to break the lone pair on the inner atom. And notice what we get. Ta-da, done. Easy. So, my opinion, a little bit easier. Not a problem to break lone pair or pairs of electrons on sulfur. You want to make your outer atoms happier at the cost of your central atom. And that's okay. We're allowed to do that because sulfur can go above 8 electrons. So that's it for today. Next time we'll talk about the one drawback with the connect the dots method, which is something that has nitrogen in the middle. Sometimes that can be tricky. So that's those are two methods to do Lewis structures. So keep on trucking, and we'll continue on Thursday. So we'll see you then. All right, take care.